Hello everybody, and welcome back to the workbench here. Just have a little project. This could be a little short video. I always say that. Hopefully it will be. On just a little project I'm building for fun. It has no purpose in life other than to waste my time and to have some fun and see how these little circuits work. And what it's called is a Tesla coil. Or actually, this is not a Tesla coil, but we're gonna it's derived from a Tesla coil. And it's a lot of looks like it'll be a lot of fun to build. In the past, I built a large Tesla coil, or I would say a medium-sized Tesla coil, in the garage when I was still living at home with my parents, much to the dismay of my parents and my neighbors and everybody else. And it was a lot of fun. I built it out of old X-ray machine parts way back in 1991, I think. So it was a good while ago. And it worked really well. Now, there is a difference between where we ended up now with this and where we started with the original Tesla coil. So let's bring in an example of just what a Tesla coil is real quick. I'm just going to spend 5 minutes real quick for those of you who aren't familiar. Okay, here we have a simplified schematic of a basic Tesla coil. Okay, this is as basic as you can get. So you have your AC mains coming in, and it goes to a step-up transformer, and this is called a high voltage transformer. And on little tabletop Tesla coils you can use like an oil furnace ignition transformer. You could use a flyback transformer from a television set if you have the right circuitry to drive it. You can also, the most common ones that you see is neon sign transformers. Any transformer that'll boost the voltage up in the 4 to 10,000 volt range, 4 to 10 kV. Okay, typically is what you see. You then go into a capacitor, which is a high voltage capacitor that obviously has to handle the RMS voltage rating of this coil. You have a spark gap, which we'll talk about in a second here. And right here is what makes a Tesla coil a Tesla coil. Okay, so the first thing you have, and if you notice, it is an air-coupled transformer. This is nothing but a transformer. You have a primary and a secondary. And unlike this high voltage transformer that has a traditional iron core, this transformer is air core, and it's designed to run at high frequencies, not at line frequency. Now, if you just took this part away altogether, like this, and you just looked at this circuit right here, this would be what we could refer to as a tank circuit. A tank circuit is a term that you hear in radio, and the tank circuit is part of a resonant circuit. Okay, it actually has a resonant property. What we're talking about with that is, if you notice, you have this spark gap. The spark gap actually acts as a switch. So as the voltage rises, so this is AC, as you can see, going in. So you're going to have AC coming out. So we start at the zero line, and as the voltage increases, when it increases to the point where this spark gap, that voltage potential from here to here, can jump that spark gap, it jumps the spark gap. And when it jumps the spark gap, this acts as a short circuit right here, which allows a current flow through this circuit right here. So what's happening is a couple things are happening all at once. Before this breaks down and draws an arc, it's an open circuit, so it's not there. As the voltage is building up on this transformer, this is a very small amount of turns, so this almost acts like just a straight piece of wire. So what's happening is this capacitor is charging, and as the capacitor charges up, once the voltage builds up to a level where there is a high enough potential for this spark gap to spark, the spark gap actuates and it dumps all the current of this capacitor through this circuit the other direction. And what's going to happen is, this is an inductor. So because a capacitor, the current leads the voltage when you induce a voltage potential across the capacitor, and the voltage leads the current. These two guys are total opposites. So in electronics you hear the old phrase Eli ice. Okay, Eli ice, meaning Eli ice. And what that means is, in a coil circuit, an inductive circuit, the voltage will always lead the current. And in a capacitive circuit, the current will always lead the voltage. In other words, the voltage starts out zero, the current starts out really high, and as this charges up and the voltage catches up to the voltage potential that's applied across it, the current will then drop back down. And the opposite happens in a coil, in an inductor. The voltage is the maximum voltage right away, and it is opposing the current until this magnetic field collapses, and then the voltage will drop and the current will increase. Okay, hopefully I explained that enough. So being that these two are in opposition of one another, what they will actually do is, when this closes, because it's arced, right? There's an arc across there, so this acts kind of like a short. The capacitor is going to want to dump all of its voltage across this. This is going to oppose the current of the capacitor, and basically they're going to play ping pong back and forth with one another. One's going to react with the other, and then it's going to react the opposite direction. The other's going to dump back in, and it will go back and forth, back and forth, back and forth at a fixed rate based upon the value of the capacitor and the value of the inductor, until finally enough energy is expended that this potential drops enough that you no longer draw an arc, and this circuit opens back up again, and then the whole process starts all over again to where this capacitor starts charging through the coil, and this just repeats itself at a consistent rate. Okay, so by setting these two things and setting the distance of this gap, we can accurately adjust at what frequency this whole circuit is oscillating. Now, why does that even matter, and why do we care about doing that? Other than having a regulated frequency, why is that important? Well, you are also creating an electromagnetic wave within this coil. This magnetic field is building and collapsing at a set period based on these component values. And if we do that, we can adjust these values such that it is at the resonant frequency of this air-coupled output secondary coil. Now, what is a resonant frequency? A resonant frequency is the frequency at which this coil will be at its maximum impedance. Let me make sure I'm saying that right. Hold on a second. Okay, scratch what I just said. Let me reword it. I don't want to say that it's the maximum impedance. It's the point at which the reactances or the impedances of these devices cancel each other out. They're maximized and opposite. So that means the point at which the capacitive reactance or the capacitive impedance and the inductive reactance are equal and opposite. They cancel each other out. And because of that, reactance is, for what we're talking about, reactance is resistance that is dependent upon frequency, I guess is the best way I can explain it without really getting into a lot of details. So when the reactance of this capacitor and the reactance of this coil cancel each other out, you end up having pretty much no resistance in the circuit other than the static DC resistance. So you get the maximum transfer of power. So with this coil, with this output, you notice there's an output which acts as a small capacitor, and this is an inductor. The resonant frequency of this secondary is the point at which all of the reactances perfectly cancel each other out. So basically, at that point, you're going to get the maximum transfer of energy from here to here. And since this is a small coil to a large coil, this is going to be a step up. And because we're dealing with high frequency and not line frequency, and we're dealing with air and not iron, the turns ratio doesn't work out the same. In other words, on this transformer, which has an iron core running at 60 hertz or 50 hertz, depending what part of the world you live, your turns ratio is going to be 1-to-1. So if I put one turn of wire on a primary and one turn of wire on the secondary, and I put 1 volt in the primary, I will get 1 volt out of the secondary. If I put 1 turn on the primary and 2 turns on the secondary and put 1 volt into the primary, I'll get 2 volts out of the secondary. That's how the turns ratio works. That does not work in a resonant transformer like this. So the gain will be an order of magnitude much higher. So what that means is we have a high frequency transformer, is what this is. So we may start out with that neon sign transformer that has maybe 5,000 volts, 5 kV, coming out of it. But by the time it achieves resonance with this coil, so these two resonate with one another, this circuit and this coil are at resonance, the output of this is going to be much lower current, obviously, because we can't create or destroy energy, okay, the law of conservation of energy. But the voltage will be much, much, much higher. So you'll have extremely high voltage, extremely low current. Whereas in here you have a lower voltage, even though it's high voltage, a lower voltage relative to this at a much higher current. So I hope that helps you to understand. Nikola Tesla devised this whole theory of resonance, electromagnetic resonance, a very long time ago, clear back at the beginning of the 20th century. And he even started devising the theories for it prior to that. So there's been a lot of controversy over Nikola Tesla and all these things, but really this is solid science here. It works. People have been playing around with this type of circuit for many, many years, and that's what this is. And people have been fascinated with them for many years. The whole concept of people trying to find that free energy and all these things, but along with some of those things is also a lot of really solid science and a lot of really wonderful inventions that have come out from this simple little circuit. So that's what a basic Tesla coil is. Now if we move forward, this is a very similar thing, and if you notice, one of the first things you see here is a long wound coil with very thin wire, and that's going to represent your secondary coil from our schematic. However, your primary coil is just going to be one little piece of wire, and I don't see it in here, but I'm sure it is. And instead of having this, and instead of having a spark gap, they do this electronically, and this is actually an updated version of Tesla Coil. It's not even a true Tesla Coil anymore. It's a circuit called a Slayer Exciter Coil. And this circuit works really well with small scale like this, but does not work very well on when you try to scale it up to large scale like you would with a Tesla Coil. The downside of a Tesla Coil is all of these things are very difficult to keep constant. As the spark gap runs for a while, the electrodes heat up. As they heat up, they ionize the air from that spark in between them, and that ionized air has a different conductive value than the non-ionized cool air that was in there originally when you first energized the circuit. And the same thing goes with these coils. As they heat up, the heat changes the properties of the wire. The other thing is moisture in the air, humidity in the air, changes the capacitive properties of these coils. And by changing the capacitive properties, you change the resonance. If you change the resonant frequency, this tank circuit has to change to match it. And since you have no way of adjusting it, the way you adjust these is by moving the spark gap further and closer. Well, you can't do that with the machine running, or you'll get a really nasty, lethal shock. So the whole circuit is unstable if you try to build it just like this. And it's very difficult to keep it for any length of time running, smoothly and accurately. Whereas with the Slayer coils, they use electronics, and you're going to see, and they're self-inductive. In other words, they're self-resonant. They're self-resonant. I'm trying to talk to myself here. It's not easy. So it's a self-resonating circuit, which means it can vary the resonance as the resonance of this coil changes with humidity and temperature and things. So it works a little bit like the jewel thief that you see in these little videos, these things that make your LED light, make your batteries last a really long time with an LED light. That's based on the same theory. It's self-resonant. It oscillates in and of itself. And as you can see here, there's a couple of little components that we use that you didn't see in the Tesla coil. So you have your secondary coil, which is this right here. You have a small signal transistor and a MOSFET. And these actually, with this coil, which is one turn of wire, this sets up a self-resonating circuit. And it uses a low voltage, only maybe 12 volts, 5 volts, low voltage. And just by running it in ultra high frequency, it can actually drive this coil into resonance, and you can get little sparks out of it. So this is not going to be as impressive as the old-fashioned gigantic Tesla coils that you see that throw lightning bolts that are 6 feet long and more. But it will put out RF high voltage similar to that of a Tesla coil, and it can do some similar things like light up a little fluorescent tube from a short distance, and things like that. And it throws the little blue spark. So they're very interesting to play with. So I thought I'd build this. That's a little nickel tour of Tesla coil. I'm sure we could do a lot bigger videos and so forth, but just keep this simple so we can play with it and see what it does. So I'm going to build this thing up, and I'll be right back as soon as I get it up and running. And in a few short solder joints and so forth, our little circuit is complete. As you can see, it's all put together. It was relatively easy. All the parts are silk screened on there, so you just kind of put it together as the board is marked out. Now, one thing I did not mention in the last scene there was that there's one extra little part to this circuit that makes it a little more complicated than a standard Slayer exciter circuit, and that is there's actually a modulation circuit in here. And if you look, there's a 3.5 millimeter jack that goes with this little included jumper wire, and this goes from your MP3 player and can plug right into here. And if you notice, this is going from this transistor, which is your oscillating transistor, over to the input, the gate of this MOSFET. And what it's actually doing is it is increasing or decreasing the amplitude of that high frequency signal. So you're basically amplitude modulating it. And by doing that, what it will do is, if you can actually hear the little spark, which we'll see if we can or not, by modulating the spark with your music, it should be able to act like a little electrostatic, like an electronic speaker, where you can somewhat hear the music. But I highly doubt that's going to work so well on this, because these are so low power. I don't know if you're going to get that much energy out of it. But anyway, I'll turn this thing on, and it runs from anywhere from 15 to 24 volts DC. I have it set up to 18 volts right now, and we're going to turn it on and see if there's any possible way we can see anything from here. Now, the first thing I'm going to try to do is douse some of these lights. So let me get that ready and I'll be right back. Alright, we are in total darkness, and you're going to need that to be able to see the output of this. I'm going to plug in the power right now. I'm running 18 volts. And as you can see, that little purple flame up there at the end is the actual output of the coil right there. See it? Okay. Now, let me turn some background light on so you can see a little bit what's going on here. And I can smell the ozone. And this is just a neon light, just a plain old neon light. And when I bring it within close proximity, you can see the light lights up with no wires. Isn't that amazing? Pretty cool. So I'm going to try to put a different electrode on this thing to get a little bit of better spark, and then we will see if we can maybe get it to sing. So let me do that and we'll be back. I've attached a little needle there, you could see, to make an electrode. It's actually coerced my wife into giving me one of her sewing needles. So thank you to her. And I epoxied it right onto here with some actual heat shrink over it. And as you notice, I have the little connector wire hooked up, and I have my MP3 turned on. Now let's see if we can get some sound. Can you hear that? It's actually working. Stop. Start. Pretty cool. That's pretty awesome. The other thing is this can burn paper, as you can see. So yeah, there it is. Pretty cool. Now I'm going to show you one of the drawbacks that comes with this circuit. And if you notice here, I've got my thermometer thing here, and if you look, 60 some degrees Celsius here, 77, and if I go to Fahrenheit, 130 degrees Fahrenheit almost. And if I look at this one, even hotter. So you can't run this for a really long time, or you will burn up these transistors. I mean, they are hot. You can't hold your finger on them. They're so hot. And that's normal. That's how they run. But as you can see, this circuit only takes maybe an hour to put together, and it works. It works really well, and even the little speaker, the little modulation circuit, works perfectly in it. So I just thought that would be something interesting to play with. I thought you would like to see something like this if you've never seen anything like it. And if you would like to build one of your own, I printed out the page from which I found mine. And let me zoom you in. And you can see the name of the seller. Of course, it's eBay. And let's see if I can focus you a little better. Name of the seller is Elex_best. And the price was US $8.91 and $1.79 shipping. And honestly, I have to admit, it came in really fast. So the shipping was very fast on it. If I move down here, you can see there's a lot of different sites that are selling it. So if you were interested in how a Tesla coil or a Slayer exciter coil works, this might be a good little inexpensive project. You only need a pair of wire cutters and a soldering iron. Not very difficult, and a screwdriver. So it's very easy to put together. They do give you a little piece of, I don't even know where it went. It rolled away. A little tiny piece of, oh, here it is. Hot melt glue, and I don't know how they expect you to melt it without a glue gun, but that they give you that to actually attach the coil form to the board. I didn't like that, so I just used 5-minute epoxy adhesive, as I did with up here for the little electrode on there. And of course I had to supply my own needle, and I did solder the wire onto the eye of the needle, so it's got a good solid attachment there. And as you can see, the modulation circuit worked. I hope you heard it. It was so quiet. I don't know if you were hearing it. We have the clothes dryer running in the background, so that may have muffled some of the sound out, but gives you an idea. So, quick little video, quick little project. I hope you enjoyed it. As always, give me a thumbs up if you liked it. This was not some big educational video or anything. You know, it was just a little fun project I was going to build, and I just filmed it while I did it. So you all have a wonderful day. Hope you were at least entertained, and more to come.